In this video, I'm going to talk about between treatment and within treatment for ANOVA. Okay, so this is more terminology and also math that you need to know. Now that you know what treatment is, we can talk about that. Okay, so what we're really doing is we're comparing the effects between treatment effects, which means the effects of treatment between groups versus the within groups variance. Okay, so we're gonna come up, now that you know that we have different groups, we are gonna have variance between the groups and variance within the groups, and are gonna compare the variance between and within the groups using the F test. Okay, so let's take a look at more information. So the between treatment estimate of population variance tells how much different groups are. Okay, I'm sorry, it tells how different how different groups are different. So this is what I told you before. So the between treatment estimate of population variances is measuring how much groups differ, and within treatment estimate of population variance tells how much within the same group people is different. So this one looks the difference between groups, and this looks the difference within groups, people in the same group. Let's take a look. So going back to my example of in our class using Excel, using half Excel and half calculator, and no Excel, just calculator. Each group is going to have different grades, mean grades, okay? And then I'm going to have an overall mean, which is the mean of the means, which is the mean of these three means, okay? So, and then I'm gonna use that to see how much the groups differ, okay? So is this group different than this group? Is this group different than this group? Is this group different than this group? So these groups can be different, and one way of measuring that is through their means, okay? How can I compute the means by hand? Is I'm gonna use this formula, which is I compute the sample size of the first group multiplied by the mean of the first group minus the overall mean. This is the overall mean, is the mean of the means. So if I sum these means, if I sum this mean and if I get this mean and multiply by the number of people, this mean and take the mean, I have the overall mean. Okay, I'm going to show you that in Excel. Okay, so this is how you compute for the first group, for the second group, the same thing, like the sample size of the second group and the difference of the mean of the second group minus the overall mean squared. So I get this difference and I square and multiply by the sample size. The same thing for the third group. If I sum them, this is what this is saying. If I sum this number, and this number, I get the sum of squares for due treatment. Okay, summation of each one of these three individual measures. Okay, and then we have the mean between treatment estimate of population variance. Okay, this is the sum, so I'm just summing, but then I can take the mean. The mean is this sum. If you take a look, this formula is the same one as this formula, but now I'm dividing by the number of groups, which is k. K is the number of groups minus 1. So if I get the sum and I get this summation here and divide by the number of groups minus 1, which is k minus 1, I get the mean variance between groups, basically, okay? And the numerator is also called the sum squared. This is the sum of squares due treatment I showed you. And the denominator is the degrees of freedom associated with this sum of squares. So this is also the degrees of freedom, okay? Now let's talk about the within treatment estimate. The within treatment estimate is how much people in the same group vary. For example, let's talk about the students that are using only Excel in my class. Some of them are gonna be more like familiar with Excel. Others are gonna be like their first experience with Excel. So some are going to be older, some are going to be younger, some are going to be more math oriented, some are going to be more like social oriented or something like that. So they vary within the same group. Okay, the same thing for all other groups. People vary within their groups. So what we're doing with the within treatment variance is we're measuring how much people in the same group, how much they vary among themselves. Okay, so I have to know how much they vary to be able to compare with how much the groups vary. Okay, so to estimate this within treatment variance, what I have to do is use this formula. This formula is the sample size of the first group minus 1 multiplied by the variance. Okay, so this is the sum. This is the sum of squared error, also called error, because it's called error because we have some variability within the same group that is a natural variance, and that's called error because we cannot control that. Okay, so each group we're going to be able to compute the variance, this estimate of treatment within each group, and then if we sum them, we have this formula here, the summation of each one of these individual within estimates. Okay, and then we have the sum, and then we can get the mean. One thing is the sum, another thing is the mean. So we can have the mean within effect, the mean within variance. Okay, which the estimator of this variance is based on the variation of the sample observations within each sample, okay, which is called the mean squared error, denoted by MSE. And if we get the sum of squares due to error, that's what we have in the numerator, is the sum of square due to error, which is the same thing here that I just showed you. And if we divide by the total sample size, this NT is total sample size. Total sample size is the number of people in this group, in this group, in this group. So I have to sum all these observations minus the number of groups. Remember, K is the number of groups. The denominator is also called the degrees of freedom associated with this sum of squares due to error. Okay. So all this information can be summarized in this table, in the ANOVA table. That's very important. We have, in this ANOVA table, we have a source of variation that comes from treatment that I showed you before, and the sum of squares is the sum of squares due to treatment. And we have a source of variation which is error, which is the sum of square error. Okay, and finally we have a total variation for these groups, which is sum of squares total. Okay, so it's important to understand this terminology and these sources of variation and what they're coming from, what they're saying. And then we have the degrees of freedom associated with which one of these sources of variation. So the degrees of freedom related to the sum of squares due to treatment is k minus 1. K is the number of groups. The source of variation due to error has the degrees of freedom total sample size minus k groups. And then we have the total sample size. Hold on, let me just wait a minute here. And okay, and then the total source of variation has the degrees of freedom as the total sample size minus 1. Okay, and if I divide, as I showed you in the previous slide, this sum of squares by the degrees of freedom, you have the mean. If you divide the sum of squares by these degrees of freedom, you have the mean squared. And if you divide the mean square due treatment by the mean square error, you get the F test, the F statistic. Remember, we had the Z, the T, now is the F statistic. The F statistic is measuring how much variability we have between groups over the error within the groups. I'm sorry. And then we're going to have a p-value associated with that. I'm going to show you one example in practice, so how we can use this table to come up with an ANOVA test. Just to finish this more conceptual part, we have, this is the conceptual overview of the sampling distribution of the sample mean, assuming that the null hypothesis is true. The null hypothesis is that the groups have the same mean. So this is what would look like if we have three groups and their means are not too different. It seems that they're coming from the same distribution. Okay, so they don't differ. What is different because there is some variability in the sample, and there's some natural error associated with that. Okay, however, if the null hypothesis is not true, so if the groups vary in their means, this is what, for example, the distribution of means would look like if the groups differ, which means AG1, the alternative hypothesis, is true. For example, one group has a very high mean, which comes from a different distribution. So it's not the same distribution as it's just two guys. These two guys, the mean sample mean 3 and sample mean 1, they overlap somehow. So we don't really know if they differ or if it's just because of variability in the sample. But this one is totally different from these two other groups. So if these two sample means represent two populations, these populations maybe similar, maybe they're kind of, we have to really understand how much they differ, but this one for sure differs. This one for sure comes from this population is totally different from this population. This is what we're testing, okay? And the rejection rule is very similar to the chapter 9 and chapter 10. If we use the p-value approach, we reject the null hypothesis if the p-value is smaller than the level of significance alpha. And in the critical value approach, we reject the null hypothesis if the F statistic is higher than the F associated with our level of significance, okay? And I'm going to show you that in more application. This is one like conceptual understanding of that. So we have a distribution, and in this case of ANOVA, we have only one tail. So we're going to have a critical value for the F associated with the level of significance we want. So if I compute the F statistic and the F is in this region, which is higher than the F critical, then I reject the null hypothesis. Okay, that's what we're talking about. There are some assumptions for analysis of variance. For each population, the response, the dependent variable, is normally distributed. The variance of the response variable, denoted as the variance, is the same for all of the populations, and the observations must be independent. Okay, so I'm going to stop here and come up with another video to show you how to use the ANOVA table.